A common method of reconstructing past climates involves the use of so-called stable isotopes. Isotopes are stable when they do not decay radioactively. The stable isotopes most commonly used in studies of paleoclimate are the constituents of water, oxygen and hydrogen. Isotopes exist because an atom can contain in its nucleus different numbers of neutrons. Oxygen, for example, commonly contains 8 protons, which is what makes it oxygen, and 8 neutrons for a total of 16 particles in the nucleus. This isotope is called oxygen-16, and it has an atomic mass of about 16 grams per mole. The numbers of neutrons in an oxygen nucleus can range from 4 to as many as 16, but nearly all of these are unstable and short-lived, decaying radioactively to fluorine, carbon, or nitrogen. One isotope of oxygen, however, oxygen-18, has an atomic mass of about 18 grams per mole, and it is stable. In the atmosphere, nearly all oxygen atoms, 99.76%, are oxygen-16. A quite small but stable proportion is oxygen-18, roughly 0.2%. The remainder is oxygen-17, but this isotope is unstable. Isotopes of hydrogen are also used in climate reconstruction. The most common isotope of hydrogen contains no neutrons, giving it an atomic mass of about 1. Nearly all hydrogen atoms on Earth are in this form. A small proportion of hydrogen atoms contain 1 proton, giving it an atomic mass of 2. This form of hydrogen, called deuterium, is stable. Another isotope of hydrogen, tritium, contains 2 neutrons, giving it an atomic mass of about 3, but this isotope is unstable and it's present in the atmosphere only in trace amounts. These isotopes can be used to estimate past temperatures. Here's one reason why. Take a drop of water, for example. This drop will contain a mixture of water made mostly from the light isotopes of oxygen and hydrogen, and a small proportion of water made from heavy isotopes of these elements. How readily these water molecules evaporate from the drop will depend upon their molecular mass. The heavier water will not evaporate and diffuse from the liquid water into the atmosphere as quickly as the light water will. This will fractionate the water in the drop, signified by a lowercase delta, with the result that the drop will become slightly enriched over time with the heavier water. This process is also dependent upon temperature. Specifically, it's proportional to absolute temperature raised to the power of 3/2. Thus, the warmer the temperature, the greater will be the fractionation. If this water drop then falls to the earth as rain, if it percolates down to the water table, it will reside there as fossil water, retaining the temperature-dependent fractionation that occurred at the time it fell. When this fossil water is sampled through, say, a borehole, the fractionation can be measured, and the temperature at the time the raindrop fell can be inferred. Another proxy measurement for temperature involves the noble gases: helium, neon, argon, krypton, xenon, and radon, shown here in order of atomic mass from lightest to heaviest. These gases are present naturally in the atmosphere, with argon and neon being the most abundant. Xenon and radon are present only in trace amounts. These gases can serve as a temperature proxy because solubilities of all gases in water increases with temperature. However, the solubilities differ between the noble gases, with solubility increasing with atomic mass. These gases will dissolve in atmospheric water drops as they form. Because argon is the most abundant, concentrations of dissolved argon at equilibrium with the atmosphere will be greater than the concentrations of neon, for example. At equilibrium, these concentrations will be determined by the gas's respective solubilities. Because solubility differs with temperature, this means that the ratio of dissolved argon to dissolved neon will also vary with temperature. When this water drops out as rain and percolates into the soil, it will carry its argon-neon ratio into the ground with it, and with it a proxy for temperature at the time the raindrop fell. There's a complication, however. Imagine a drop of water in equilibrium with the noble gases in the atmosphere. There will be a certain argon-neon ratio that will serve as a proxy for temperature. When the drop falls out of the sky, however, it falls with a certain kinetic energy proportional to the square of the drop's falling velocity. As the drop strikes the ground, this energy is dissipated as distortions of drop shape, driving the drop more forcefully into the soil and incorporating bubbles of air under pressure into the drop. All this will act to drive both argon and neon more forcibly into the drop, elevating the dissolved concentrations of both argon and neon to higher than their equilibrium values. This elevation is known as excess air. The amount of excess air can distort the noble gas thermometer, which must be corrected for. However, the excess air also provides a proxy measure for how energetic a rainfall is. If there is little excess air, rainfalls are gentle. Torrential rainfalls are marked by increased excess air. And what has all this to do with Namibian paleoclimates and the question of the age of the Namib? These techniques have been used to estimate temperatures and intensity of rainfalls over the past 40,000 years. These efforts involve analyzing fossil water from the Stumpreet Aquifer, which underlies the watersheds of the Awab and Nasab rivers. The Stumpreet Aquifer spans much of southeastern Namibia, as well as parts of South Africa and Botswana. Borehole water from the Stumpreet Aquifer supports agriculture and livestock farming in this region. Turning to regional temperatures, the noble gas temperature of this fossil water shows a marked warming beginning about 12,000 years ago. This corresponds to the end of the last ice age, which was at its worldwide peak at the last glacial maximum, roughly 26,000 years ago. As the Earth emerged from the latest ice age, deglaciation in the northern hemisphere began roughly 20,000 years ago. Deglaciation lagged somewhat in the southern hemisphere. Even though Africa itself never experienced any glaciation during the last ice age, Antarctic deglaciation commenced roughly 14,000 years ago. So, this marked warming from an estimated temperature of around 21 degrees Celsius, up more than 5 degrees to more than 26 degrees Celsius, reflects the global warming that accompanied the end of the latest ice age. Turning back to the issue of rainfalls, neon enrichment can signify the energetics of rain falling during these times. And here is what the 40,000-year record reveals of that. During the last ice age, rainfalls were of moderate intensity, but for a span of time roughly 6,000 years ago, neon enrichment was high, signifying that rainfalls at that time were energetic. That is to say, the rains were probably torrential. Only in the past 6,000 years has the climate dried to the arid conditions that prevail today. The conclusion? Regional climate has, in fairly recent times, been much wetter than it is today. In all likelihood, the Namib was, as little as a few thousand years ago, a much wetter place than it is presently.